Mossy Creek is a natural limestone spring creek which meanders 8 miles through the Shenandoah Valley and is one of Virginia's most famous fly fishing destinations. This area is full of wildlife with various aquatic vegetation and is best known for their brown trout population. The problem at Mossy Creek is that it is prone to flash flooding, which causes property damage, erosion of the natural creek banks, and disruption to wildlife. This flash flooding creates heavy debris buildup against pre-existing bridges, which cause them to fail and break down. Our team is interested in this problem, and we're working to provide local and visiting fishermen, as well as community members, access to a bridge that can withstand future flooding events and provide them a means of crossing the creek. We are Crossing Streams, a group of diversified engineers looking to make a difference in the local community. Our values consist of, but are not limited to, respecting all of those with whom we work with, demonstrating genuine teamwork, holding ourselves and each other accountable, and having fun. Each teammate has interests in the aspects of civil and environmental engineering, and we all bring different backgrounds and experiences, which allow us to act as one cohesive group in which communication is effective and one in which we all learn from one another. Our team came together in the fall of 2019 to begin this project, almost 1 year after one of the largest floods recorded in the history of the Mossy Creek area. This flood caused many issues throughout the community surrounding Mossy Creek. It blocked roadways, caused structural damage, and washed away residents' backyard bridges. This flood in particular took out many of the residents' bridges living along the creek, washing these bridges several hundred of yards down and up onto the creek banks. Without these bridges in place, fishermen are unable to access the banks on either side of the creek, and residents lose their method of transportation across it. Residents who had their bridges washed away would normally wait until the waters had calmed and lowered and use machinery to carry these bridges back up to their original location. However, when this catastrophic flood in 2018 hit, most bridges ended up like the one depicted in the following slide. Destroyed and irrecoverable. This bridge was made of four 40-foot long telephone poles. This was a big bridge, and it was washed over 300 yards from its original location. Bridges like these could survive small-scale flooding events. However, they weren't built to handle heavy flooding conditions. This is the problem our team aims to solve. We aim to design a bridge that can withstand any type of flooding condition. To solve this problem, we've been split into 3 teams in order to design a sustainable, durable bridge. Team A, which is responsible for the creek bank and bed rehabilitation. Team C, which is responsible for the bridge deck and superstructure. And Team B, ourselves, who are responsible for the abutments and to serve as the connection between the other 2 teams. Our team, Team B, must be in constant contact, working with both of the other 2 sub-teams to best support the span, vehicles, and people that may cross in order to make sure the abutment is suitable for the soil type. This is a complex problem, especially for our team, because we must meet the requirements and constraints from both of the other sub-teams within our design. Now you may be asking, what is an abutment? Well, an abutment is a structure built to support the span from a lateral load, built to support the load from a lateral span. Let me correct myself. An abutment is a structure built to support the lateral load from an arc or span and is used to transfer that load into the ground that it's resting upon. They're typically located at the end of arches or spans, however, will be visually highlighted in the following slides. So this sketch shows a basic bridge. On the far left in the dark gray is what I explain as an abutment. This is what takes the load from the superstructure and delivers it into the ground. There are many different variations and designs for an abutment depending on the situation at hand. The superstructure and deck are the 2 long pieces that stretch from the abutment on the left to the abutment on the right. The stronger or heavier lower piece being the superstructure, and the deck being the thin layer that rests on top of it. There are less variations for bridge decks and superstructures, however, still a few that must be considered given a situation. Now let's move into real-world bridges. Pictured above is the Golden Gate Bridge. What an incredible structure built over such a long span. I mean, this is what engineering is really all about. Now you may be thinking, yeah, it's just a bridge. But take a minute and really think about all the calculations, careful planning, and complexities that went into designing this bridge. And not only this bridge, but every bridge ever built. Because all bridges serve the same function to allow access from one side to another, they all have similar concepts in which can be compared to one another. Shown above is a current bridge over Mossy Creek. This is the scale at which our team will be designing at. Although our design is much smaller in comparison to the Golden Gate Bridge, it will have the same features and serve the same purpose. This is why our project is so interesting and holds such a variety of complex features. By comparing our problem to those that have been overcome, we can gain some very valuable insight. After learning about specific bridges, their components, and their significance, our team began to brainstorm and design different abutment systems. The team spent weeks generating possible design solutions and comparing them to requirements that must be met in order for the project to be successful. The top picture, design concept number 4, is one of the many design concepts that the team had generated. This concept features a shallow yet wide abutment that is driven into the ground made of concrete and steel rebar, which is just short for reinforcing bar. The bottom picture, design concept number 13, is another design that uses cylindrical wooden piers to support the superstructure and give the bridge a substantial amount of room over the water. These are just 2 of the many designs the team has generated and will continually be tweaked and adjusted until the team determines the most viable design. Our plan moving forward. Our team anticipates the return to JMU's campus come the fall of 2020 to continue this project. Once we return to school, we will begin looking into how different geometric abutment designs affect the design's overall strength, as well as how we might design a unique and novel bridge that rotates about its foundations, most comparable and similar to that of a drawbridge. Again, we are Mossy Creek, Team B. Thank you for your time, and now we would be happy to answer any questions you may have.